Hi, Science 30s. So this is the, I believe, fourth lesson in Unit D, Energy. And in your notes package, it will say at the top, nuclear fission. So hopefully you completed those kind of set of questions on the pages before that related to radioactive decay and kind of the types of nuclear reactions that we started with. So on that nuclear energy page, we said 3 types of nuclear reactions exist. So radioactive decay, and that's including transmutation, and then fission and fusion. So we'll do a quick lesson here on fission, and then the last lesson will be related to fusion. And then you will have your unit test on Friday on all of energy. So that's both chapter 1 and chapter 2. So you'll need to go back and study back into that chapter 2 stuff related to our renewable and non-renewable sources of energy and kind of looking at how sustainable those technologies are in environmental, economic, and societal sort of ways. So have a peek back at that, and then you'll do your last unit test that we're doing because we didn't do the physics unit, and that's totally fine. So nuclear fission. Scroll on down. I guess we should full screen. So nuclear fission, so keep fission and fusion separate in your mind. They're pretty darn close in terms of the words. But nuclear fission is the process by which a large mass nucleus splits into 2 or more smaller nuclei along with the emission of neutrons. So the product of this, there'll be the product of some amount of neutrons, a couple of neutrons, and it will be taking something that has a pretty large mass. So fission can be induced artificially by bombarding an atom, such as like uranium-235, plutonium-239, with neutrons. And so it's like firing neutrons at it. And what it actually does is breaks it into fragments. So the example that we have there, sorry, it's kind of offset on your notes potentially, is taking uranium-235. So again, that 235 is the atomic mass. So it's some type of isotope of uranium, bombarding it with neutrons. And what we see is we get 2 fragments, or 2 parts that they just represent as N1 and N2 here, and neutrons. So uranium-235 is being split into smaller mass things. So barium-141 and krypton-92. And what we see is our last product is 3 neutrons. So my N1 and my N2 fragments are these. So it's splitting something that has an overall mass of 92. Yes, into something. So if you look here, 56 plus 36, if you punch that into your calculator, it's equal to 92. And if we added up 141 plus 92 plus 3, because again, it's 3 of these, that would add up to 235. Ooh, that doesn't add up to 235. Let me just bust out a calculator. So 141 plus 92 plus 3 is 236. Oh, like that doesn't add up, but that makes sense because 1 plus 235 is 236. Now that makes sense. So N1 and N2 are called fission fragments, and they usually are roughly about half. You see that this is not exactly half, so 92, 56, and 36. So it's somewhere around half. So you're not usually going to get a fission fragment that's like if we started with something, sorry, we're talking about the mass, not the atomic number. So the mass, 141 and 92. See, we wouldn't start with uranium-235 and end up with one product that's 13 and then another product that's way more than that. Usually it's somewhere around half. So these numbers are close-ish. You won't ever have to predict the products of a fission reaction, so don't worry about that. So typically there is usually somewhere in the range of 2 to 4 neutrons emitted. We also sometimes actually have beta particles that are emitted by that. So back to beta particles, when did we do that? So that was before harvesting chemical energy, wasn't it? Nope. Oh, yeah, it was in the last lesson. I thought it was before that. So a beta particle kind of looks like an electron. Um, so having the same charge and mass as an electron. So the release of energy. So in this reaction, the other product that we could put is energy. And we could put a whole bunch of flashy stuff around it to indicate that there's lots of energy that's released within this. So the release of energy occurs due to a mass difference between the products and reactants. So we've always talked about the law of conservation of mass, that like what goes into an equation is coming out of an equation. In this case, though, it's kind of tying to Einstein's special theory of relativity. And so what it's saying is this energy actually comes from mass. So some of the mass is converted into energy, and energy could be converted into mass as well. So the amount of energy that can be released or is released can be calculated using that formula that everybody says to pretend they're smart, but most people don't actually know what it's talking about. So this is called the mass energy equivalence. And so delta E is your change in energy, so measured in joules. Your mass is the change in mass measured in kilograms. So the way that we find delta M, so change in mass, is your mass of your product subtract your mass of your reactants. So how much energy or how much mass needed to be lost, quote unquote, which is actually converted into energy. And then C is the speed of light. So this is how fast light can travel in a vacuum. So 3.00 times 10 to the power of 8 meters per second. And that's going to be a constant. So you'll use that number in all of the calculations, but your masses will change, which gives you a difference in energy. So this is this part here. So it says this is information about the efficiency of nuclear fission. So it says, FYI, a 7-gram pellet of uranium. So a 7-gram pellet of uranium would be very small, like easily fits in the palm of your hand. And a 7-gram pellet of uranium can release the same quantity as 556.5 liters of oil, 480,000 liters of natural gas, or 807 kilograms of coal. So this tiny little piece of uranium can do as much as just a nice amount of oil, a lot, tons of natural gas, or just a giant amount of coal. So efficiency-wise, it's awesome in that it can release a lot of energy per unit. Okay, so some practice problems using the mass energy equivalents above. So in the fission of 1 more mole of beryllium-8, the mass of the products is determined to be 2.29 times 10 to the power of -5 kilograms less than the mass of the reactants. Calculate the energy change that corresponds with this change in mass. Identify whether the reaction is endothermic or exothermic. So the one thing is, these are all going to have pretty small mass differences. So 2.29 times 10 to the power of -5 kilograms, that's like way less than 1 gram of difference between your reactants and products. So they're usually going to be pretty small amounts. It would be a little bit wild to have a really huge mass difference. So just thinking about what we know. So delta M, so change in mass, is that number that we had above, 2.29 times 10 to the negative 5 kilograms. C is that speed of light constant, 3.00 times 10 to the power of 8 meters per second. And delta E is our question mark, because it's saying calculate the change in energy that corresponds with that mass. So delta E equals change in mass, delta M times C squared. Again, the squared actually only applies to that C value. So make sure you don't, if you're using a scientific or like a regular calculator, not a graphing calculator, you got to figure out how to put brackets in and stuff like that, because your calculator will do things in weird orders if you give it the opportunity to. So just substituting those values in. C and so that 3.00 times 10 to the power of 8 is what's squared. Then you would multiply it by this. Oh, I did this different in my notes. I actually called this the change in mass as negative 2.29 because it's 2.29 times 10 to the power of negative 5 kilograms less than the mass of the reactants. You can do it that way, or you can just express it at the end that it's going to be an exothermic reaction, because like if I do this as a negative, I get negative 2.06 times 10 to the power of 12 joules. Make sure you put that in your calculator and make sure you get to the same answer, because if you're messing up this squared thing or not able to put in your scientific notation properly, these questions can get pretty hard. So this is an exothermic reaction because, again, since the mass is less, that means that mass, so mass needed to be converted to energy. That says energy, I think. So the next question, the fission of uranium-235 that occurs in a CANDU reactor. So I believe in the last set of questions, oh no, maybe CANDU was in, oh no, you would have learned about the CANDU reactor in chapter 2. So, so this is the reaction that's occurring. So again, uranium-235 bombarded with neutrons splits into what we had above. So that reaction that we saw above. So barium and krypton, and also the production of some more neutrons. It says calculate the change in mass between the reactants and the products for this reaction and the corresponding energy change. So this, you need your data booklet. Sorry, I'm just searching my pile of stuff that I have. So this one, you're not actually given the mass difference. You need your data booklet. Pause and find your way to it. And flip your way to page 8. It says nuclear chemistry at the top. So what we need to do is we need to calculate out, since we're not given anything, the mass of the reactants and the mass of the products. Then finding the difference between them will give us this delta M. So delta M, again, is equal to the mass of your products subtract the mass of the reactants So now we need to figure out both of those pieces of information. And so, oh my gosh, I did not leave myself enough room here. So the mass of the reactants is going to be the mass of the neutrons. Oh, sorry, reactants is the mass of the uranium plus the mass of one neutron. So this chart, it's like in the middle of the page there, it says masses of selected nuclides, and then at the top it actually has the masses of subatomic particles. So the mass of uranium, if you look for it, so uranium-235, this is just a little bit more precise of a measurement, and you need to use these precise measurements because, again, those small changes in mass actually represent a pretty big change in energy. So we need to use these more specific values. So again, that's sorry, I'm just trying to figure this out. So our balanced equation, like the only thing that has a number in front of it is this 3 neutrons, so 1 mole. Actually, I'm not even going to do that. I'm just trying to save some space. So the uranium is 235.05. Oh, what am I doing? 235.04392. So that comes from the chart. Times 10 to the power of -3 kilograms. That's like per 1 mole, and we have 1 mole of it. And then the mass of a neutron, there's only 1 neutron, so that's 1.00866 times 10 to the power of -3 kilograms. So our mass of our reactants is equal to 236.05258 times 10 to the power of -3 kilograms. The mass of the products so our products is what's produced. So mass of 3 neutrons, I'm doing this in the wrong order, plus the mass of barium plus the mass of krypton. So 3 neutrons, so 3 times 1.00866 times 10 to the -3. Mass of barium, again just 1 barium, so that's up at the top, so 140.91441 times 10 to the -3 kilograms. Sorry, I just tried to put a bracket around it and I just kind of got rid of my 1. And the mass of krypton, so 91.92611 times 10 to the power of -3 kilograms. So our mass of our products, if I've written everything out right there, just double checking. So our mass of our products is 235.86650 times 10 to the power of -3 kilograms. So now we have our mass of our reactants, oops, and our mass of our products. So now we can insert both of those into this formula. So mass of products, subtract mass of reactants, gets us. So I'll write it all out just in case. So 235.86650 times 10 to the -3. Subtract. Hopefully you have more room than I did. 236.05258 times 10 to the negative 3 gets us, sorry, I know this is a hot mess right now, a delta M, so that's our change in mass, equal to negative 0.18608 times 10 to the negative 3 kilograms. So from here, now we can do our change in energy. So change in energy is equal to change in mass times the speed of light squared. So, sorry, I just have no room left. So 3.00 times 10 to the power of 8 meters per second. That whole thing is squared, multiplied by negative 0.18608 times 10 to the negative 3 kilograms. Gets us a change in energy of negative 1.6747 times 10 to the power of 13 joules of energy. So that's a lot of energy being released. So the energy released, again, because it's a negative value there, from 1 mole of uranium-235 is 1.67 times 10 to the power of 13 joules. Lots of energy released. So I'm just trying to think if there's some videos that give a little bit of just a better visual for something like that. Fission, reaction, animation. Yeah, you can probably kind of look at, I always look for ones that have lots of views. This might be complex, but might have a good visual. I was hoping there would be, oh, chain reactions. I think I have something about chain reactions in here. Oh, nuclear chemistry crash course. That might be a good one to look at. You know how I feel about Hank Green. Probably has a little bit, it's probably a little bit more in depth, but he explains it in a way that usually makes quite a bit of sense. You might want to look up this crash course on nuclear chemistry. I think, oh yeah, so there's some practice problems from the textbooks, but there's a little bit more. So there's a space there, that's why there's a big space on the page, is you can do some of those practice problems there. Just a little bit more. Oh, maybe can do is here. Sorry, I'm getting my whole life together right now, guys. You're welcome. So fission reactions can be self-perpetuating. So the neutrons that are released in a fission reaction can bring about fission of more uranium-235 atoms. So when we look at what's happening in that CANDU reaction, these neutrons can bombard additional uranium-235 atoms and create more of this reaction. And so that can be good if you want to say that, but it can also be a bit of a problem. So this is called a chain reaction. And there's two types of chain reactions. So we can have an uncontrolled fission chain reaction. So where it just self-perpetuates and gets super out of control. So energy released is almost instantaneous. The reaction rate increases exponentially over time because, again, you have so many neutrons being released that can create the next chain reaction, right? So a very good example of this is the atomic bomb dropped on Hiroshima and Nagasaki in 1945. Within that atomic bomb, there was uncontrolled reactions. Not great. But you can also have controlled fission chain reactions. And so this is used in nuclear facilities to provide electricity. So the rate of the fission chain is controlled with the reactor to give a constant number of fissions per unit time. And so the energy conversions within that, so that stored nuclear energy as it's released, it's going to heat up. Usually it's going to be water. So heat up water, it produces steam. The movement of that steam as it rises produces kinetic energy, and that probably turns a turbine, which will generate electrical energy. So good situation, bad situation. Because again, that significant release of energy can be a real problem, but if it's controlled and can be harnessed, well, then we have a pretty good source for electricity. So now that I've talked a lot about the Kennedy reactor, now you can go look it up. So in your textbook, in a couple of questions, what is actually happening within a nuclear power plant versus coal burning power plant? So that's it for this lesson. The next one will be a little bit shorter. It'll be very short, in fact. You know what? I'm just going to keep going. I was going to stop, but we're only at 26 minutes and it's one more page. So let's just finish her up. So nuclear fusion. So occurs, so fission, again, was breaking it apart. This is fusion. So this is looking at when two nuclei with small masses combine to form one nucleus with a larger mass. So I don't want to say the opposite, but it's kind of the reverse process in a certain way. So the mass of the newly fused nucleus is smaller than the combined mass of the nuclei that formed it. And again, this mass difference results in the formation of energy. So the mass of the two first pieces is less than the mass of the third piece after the reaction. So we know that that energy mass difference, or this mass difference, results in the formation of energy. So this is important to us. The sun's apostrophe? Yeah, maybe. Perpetual energy is generated by nuclear fusion, and thus fusion is the source for almost all the energy for the natural physical and biological processes on Earth. So the energy that we have stored in the food we eat and in our petrochemicals, that came from the sun. So fusion reactions are very important. But in order for a fusion reaction to occur, it requires very high temperatures where elements exist in the plasma state. So existing stripped of electrons and exist as bare nuclei. What is going on here? Can't fix that. So if these positively charged nuclei can be brought close enough together, the strong nuclear force, we talked about that already, between them may pull them together and fusion could occur. So again, what you need is high temperatures to strip it of electrons. You need to bring them so close together because that strong nuclear force operates over a very short distance. So you need to get it very close together because remember, these positively charged nuclei naturally are not going to want to be near each other just due to the electric charge between them. So it doesn't want to happen, but if you can get them close enough together, the strong nuclear force may pull them together and fusion could occur. So the proton-proton chain in the sun results in the following net reaction. So this is what's occurring within our sun. So we have one hydrogen and, oh, sorry, the following net reaction. Yes, that makes sense. Not one hydrogen, four hydrogens fusing together to produce a helium, an electron, a beta particle, but also this. We talked about this the other day. So gamma rays. So gamma rays, ionizing radiation, can create some problems, but very high energy. So for equal masses of reactants, fusion yields somewhere between 3 to 10 more times or sorry, times more energy than fission. So I had that example about the uranium pellet and the significant amount of energy that was released from it. Well, fusion is even more significant than that. So more energy can be released. Sorry. So the first fusion bomb is commonly called the hydrogen bomb or the H bomb. And it was detonated in 1952 and uses fission to generate the temperatures. So it used fission reactions, the previous one that releases a lot of energy, to generate the temperatures required for fusion. So it used fission to create what was needed for fusion. So to date, attempts at hot fusion have failed to generate more energy output than input. So it was requiring more energy to get it started than it actually released. And any attempts at cold fusion, so that's fusion at room temperature. Again, I've said it needs to be really, really hot, really, really hot. So cold fusion have been unsuccessful. And so I'm sure there's a really good, oh, fusion and fission. So I would watch that crash course. It will talk about both of them. Will be some good visuals of what's actually happening and a little bit more of the history stuff. I'm glad I did that. That was only 5 minutes. That would have been a silly lesson to do on its own. So I don't know why that's there. That's from the fission part. But a couple more questions from the textbook. And then just a little bit of review. I sent those review questions. And from there, you're ready for your Unit D test. Thanks, guys. We'll chat with you later.